I will begin with a word of prayer. Dear Father, we thank you for this day. Thank you for the spring break that's about to start. Just help us to have a good class today, Lord. In your name I pray. Amen. Let's see here. Yes, happy spring break. Very, very nicely written, but I must destroy it. So, a couple things I wanted to do today. One was just to go back and talk about the quadratic extension calculation. Hopefully that won't take us too long. I think it's just like a 5-minute calculation, famous last words, right? And then I wanted to look at the mechanics of the cyclotomic polynomials, because it's really kind of neat. There is a way to generate them. And the connection with number theory is also intriguing. Okay, so let me begin with the example from page 522. Here it is, F, a field with characteristic not equal to 2. All right. And he says, let K be any extension of F of degree 2. What was that? Oh, okay. Cool. Any extension degree 2. And then he says, let alpha be an element of K, alpha not be an element of F. So look at something that's in K that is not an F element, all right? Then he says, by the proposition above, alpha satisfies an equation of degree at most 2 over F. Right? Remember well, it's a little bit since we did it, but if you go back to the proposition, I think this is the one I did AB, proposition 12. That's the one I broke out into parts. So that proposition shows us that the degree of alpha has to be at most what? So like the minimal polynomial of alpha over F of X has degree what? Less than or equal to 2. But of course it cannot be degree 1, because if it was degree 1, that would mean alpha's an F, right? So that implies the process of elimination here, that the degree of alpha is just 2, all right? So what's that mean? So the minimal polynomial of alpha has to have the following form, right? X squared plus bx plus c, where b and c are in F. He says, since F is a subset of F adjoint alpha, which is a subset of K, and the degree of F alpha over F is equal to 2, that implies, of course, that F alpha is what? Yeah, he says K is equal to F alpha here, because we picked alpha in K, so yeah. Let's see here. So what? Then the question is, what does this alpha look like, right? And his claim is that we can look at alpha as being like a square root right? So he says that, okay, so suppose you want to calculate the roots of this. He claims that we can basically go through the quadratic formula over an arbitrary field, as long as the characteristic is not 2. Let's go through those steps, yeah? So if we're looking to solve x squared plus bx plus c equal to 0, I can do, that's x plus, and b over 2, right? So b over 2 squared is what? That's x squared plus bx plus b squared over 4, right? That's assuming that the characteristic is not 2, so that 2 has a multiplicative inverse in the field, right? But this is an identity, right? Thus, x squared plus bx plus c is equal to x plus b over 2 squared minus b squared over 4, right? Plus c. And if we set that equal to 0, we can rewrite this as x plus b over 2 quantity squared equal to what? B squared minus 4c divided by 4, using laws of arithmetic in a field. Again, characteristic not 2, so 4 has an inverse, multiplicatively speaking. And then, so alpha has to be alpha should be like a root to that equation. And I think the steps I've done have not, none of the steps that we've done have removed any solutions, right? I mean, is that the right way to think about it? Well, he says that the quadratic formula is valid over any field of characteristic not equal to 2. So let's see here. Then I think then the idea is to I guess what I should say is by assumption, right? We have that what? Alpha squared plus b alpha plus c is equal to 0, right? Because it's the minimal polynomial for this element alpha. But by the algebra I just went through with x, you can just as well go through with alpha. And that tells us that alpha plus b over 2 squared is equal to b squared minus 4c over 4, right? So alpha is this element such that if I add b over 2 to it and I square it, then I get b squared minus 4c over 4, right? So we just use the square root to denote a possible solution to this. So this is equal to the square root of b squared minus 4c over 4. And of course, you could have put the 2 to the other side. I mean, if you think about it, it's not a big jump to put the 2 outside the root. Okay. So therefore, alpha minus b over 2 plus 1/2 square root of b squared minus 4c. But he's careful here. He says that the square root doesn't necessarily mean the square root that you're accustomed to. It's whatever square root means in your field. And that could be different. Like, it's not necessarily the positive square root. He's using square root for a notation for a possible solution in my arrow equation, you know? And Like you said, there's no natural choice for one of the roots in an arbitrary field, not like R. Of course, in the reals, we can always pick the positive root, right? For the square root, quote unquote square root is the positive root. But he says, it follows that f adjoin alpha is equal to f adjoin the square root of b squared minus 4c. Or I guess to start with, he might say subset. Well, he gives an argument for this. All right, he argues why that's true by arguing double containment. So let's just walk through it briefly. How can you see that f alpha is a subset? How can you see f alpha is a subset of that? So if we look at f alpha, right? That has alpha in it, right? And so, 2 alpha plus b equal to the square root of b squared minus 4c, yeah? So if I have alpha, I can multiply by 2, I can add b, everything's happening inside the field, which is inside here. And what have I done? I've built the square root of b squared minus 4c. Therefore, this is a subset of f adjoin the square root of b squared minus 4c. How about vice versa? What if we start with the square root of, f adjoin the square root of b squared minus 4c? How do we get that as a subset of f alpha? Because we can also argue that. Enough of this marker. It's garbage. Whoa, that was close, Kirsten, excuse me. What's wrong with me? You'd think I'd learn a person's name eventually. It's Kristen. Yeah. Good grief. Well, I should have stopped while I was ahead. I could redeem myself by ending class right now. That was a psych. So I should not. Don't get too excited about that. Hey, wait a minute. I should redeem the time. 7, 8. Okay, there we go. So on the other hand, of course, if you have the square root in your field, well, then you can divide it by 2 and subtract b over 2, and that gives you alpha. So that means that this is a subset of that. And by double containment, they're equal. So this is why if you have a degree 2 extension, we can always view it as adjoining the square root of d, where d is not a square in the base field. Right? We've used this a few times here and there, but this can be, this is a generic argument. It's kind of neat. I like this argument. I like going through the quadratic formula and appreciating how stupidly general it is. I especially like that, it's so funny that if you have z squared plus bz plus c in the complex, it is still true that z is equal to, minus b plus or minus the square root of b squared minus 4c over 2. But the funny thing is that b squared minus 4c, these is equal to, as a set, the principal square root and minus the principal square root, because the second root of unity happens to be minus 1. So it's just a quirk of the way complex equations are solved, that the the set of half powers, this collection of second square roots, if you will, b squared minus 4c is obtained by just doing plus minus. And so the traditional formula that you learn in real algebra is still true in the complex case, but you got to understand that these are principal roots. So like if b squared minus 4z is 3 plus I, well, let's say 3 plus 3i, you got to look at that as 3 over the square, 3 root 2 times e to the pi I over 4, right? And so like the principal root of b squared minus 4c, it's, well, what is it? It's the square root of 3 times the square root of 2 times e to the pi I over 8. You know, you got to understand, this is not what you learned in middle school, but it's still correct with the proper understanding of what square root means in the complex numbers, which is principal square root. I think it's really neat, yeah.
So you said that b squared minus 4c has to be something that, so like it makes sense in the real numbers, it's not a square.
Yeah, we need b squared minus 4c is not equal to d squared for some d in the field, right? What would happen if b squared minus 4c was equal to some d squared? What would that say? Yeah, exactly. If b squared minus 4c was equal to d squared, that would mean that the solution to the square root was given by plus or minus d, I think. What? Just something. If there exists something in the base field such that the square was the inside of the square root here, that would mean that this formula is not something outside of f. This formula would take you back to the field again, and we would violate the initial assumption, which was that alpha is not an element of f, making this thing, the thing inside the discriminant, as it's called, right, a square, spoils the initial assumption that the extended element's not in the field.
So the fact that there's like not something in front of the x squared in that equation, why do you like leave out like the a term from the quadratic formula?
Right. Yeah. Because.
So if there was something there, you would put it in like normal.
Yeah. Oh yeah. Oh yeah. We could put an a there, and then it would clutter the formula like usual.
Okay.
But the reason for our current focus is because the minimal polynomial is assumed to be monic, and so that's where we have all the theorems. It was our definition of minimal polynomial. It's the unique monic polynomial of least positive degree for which the what is our definition of minimal polynomial? Yeah, alpha is a zero of it, and it's the smallest degree, right? And monic, because otherwise there would be more than one. Yeah. Because if m of x works, then 17 times m of x still works to give alpha a 0, and it's still the same degree. Yeah. So let's talk about cyclotomic polynomials. I'll try to keep it brief since the spring break must start, right? Let's see how much time I have. Come on. Come on. All right. We should be okay. So this is section 13.6. We'll be okay as long as I don't try to prove anything. Cyclotomic, I'm sorry we lost the video from last time. My clear and lucid proof of the generalized Eisenstein criteria. It's so sad that that's lost to the problem of technology. Although the rest of class last time was actually pretty good. I'm kind of annoyed that we lost it in extensions. I think we had some good discussion last time as a thing. Oh well. You guys were here. That's all that matters. Cyclotomic polynomials and extensions. So, first of all, let's recall nth roots of unity, right? Let's see here, zeta n is what? Is that a specific thing, or is that a... What is this zeta n? Does that have a fixed meaning in here? I think it does. I think this is e to the 2 pi I over n, if I recall correctly. So if we take q adjoin zeta n, right, this over q is degree what? So the big result of this section is explaining why the degree of the cyclotomic field of order n is actually what? phi of n, yeah. So we looked a little bit at the case that n was a prime and studied that and something about that in the previous class, right? So let's talk about that a little bit. Let me just say a few things. Definition, he wants mu n to be the nth group of nth roots of unity. What's that?
What's the first one?
Mu? Mu?
Is that
Kappa?
capital? Capital?
Capital mu. I don't, mu.
Doesn't mu have a look? It looks like a U with just like a tail on one side.
Oh, you want me to do this? Am I mu always?
I've just never seen it written that way.
Oh, I always write mu that way. I don't know. My lambda is also wrong. That's comforting. I write lambda. That's not lambda. Lambda is this. My mu is basically an upside down h. Yeah.
I feel like the two.
Okay. Now, so group of unity, roots, nth roots of unity over Q. All right. And he says that he's already shown Z mod NZ is isomorphic to the roots of unity, right? And the isomorphism is what? A maps to zeta n to the A. That's a homomorphism because, you know, the ambiguity in the choice of representative in Z mod NZ is squashed by the fact that Zn, that's supposed to be a zeta. My zetas are degenerating. It's getting worse. It gets worse every time. That to the nth power is the identity, right? So it makes sense, this isomorphism. He says, for a fixed primitive nth root of unity. Oh, he does use zeta n as like an arbitrary nth root of primitive. His note, like he's thinking of zeta n as an arbitrary primitive nth root of unity. I made the specific choice, e to the 2 pi I over n, but there are other choices in his view for what zeta sub n should be, you know? But let me focus. He doesn't write this. He just says that zeta n is a primitive nth root of unity. So if n was like 4, you could also do e to the 2 pi I over 4 to the third power. You know, you could either use I or minus I as a primitive fourth root of unity. All right, getting to the point here. He says the primitive nth roots of unity are given by residue classes prime to n, so there are precisely phi n primitive nth roots of unity. Remark. There exist phi n primitive nth roots of unity. Here, I'll even tell you what they are. E to the 2 pi I over n to the j power for j where? Yeah, j and mu n, the units, right? Okay. I guess I should say in mu n here, right? Because he's calling it mu n, right? Okay, great. He says, if D is a divisor of n, then zeta, and zeta is a d-th root of unity. I need some. Room to write. So he said, what did I just say? I said, D is a divisor of n. My mind. D is the divisor of n, and zeta is the dth root of unity. What's it mean for d to be zeta to be a dth root of unity? That means that zeta to the d power is equal to 1, right? Okay. And then he says, since zeta to the n, what's zeta to the n equal to? He points out zeta to the n is zeta to the d to the n over d. Zeta to the d to the n over d. N over d is what? I mean, it's an integer, right? So this makes sense, because if d divides n, then n over d is a number, whatever it is, who cares? Zeta to the d is, by assumption here, 1. So 1 to the whatever, it's still 1, right? Which says what? Zeta is also an nth root of unity. Okay? Also an nth root of unity. And so he points out that mu d is a subset of mu n for d dividing n. All right? And he says, conversely, the order of any element... Whoa. Well, I won't miss any calls. You won't miss my calls either. I hope not, over break. If you got my calls over break, it'd be kind of creepy. Let's see here. It'd be somewhat disturbating. Let's see here. To use a technical term. Uh-oh, my time is waning. Tick-tock, tick-tock. Let's see here. So, where are we? Conversely, the order of any element of the group, you notice, so if we have, let me just say, if x is an element of mu n, then the order of x must divide n as well, right? Because if it's in a group and the group has order n, we know the theorem that the order of any element must divide the order of the group, right? Because the group generates the cyclic subgroup with the same order as the element, and that's a subgroup. So by Lagrange's theorem, it must have order which divides the group. Yeah. So just a little bit of group theory to remind you. What's his point? He says, so that if zeta is any nth root of unity, which is also a dth root of unity for some smaller d, then d divides n. I've lost something here. I don't he's using d like a very, whatever. Definition. The nth cyclotomic polynomial all right, which we will denote phi n of x, is the polynomial whose roots are the primitive nth roots of unity. So at this point, it should be immediately obvious why. Assume for a second that this is an irreducible polynomial over Q, right? If it is, what's its degree? Degree, not n, no. What's the degree of phi n of x? How many roots does it have? The roots are the primitive nth roots of unity. right? It's the number, it's the cardinality, if you will, of mu n, right? It's the number of, which is what would you say? Which is phi of n, right? So if we already had proved, all right, that phi n of x was irreducible, then that would establish the claim I made at the start, namely that the cyclotomic extension, because then q adjoins zeta n is the extension that is, isomorphic to taking polynomials in q and quotienting by phi n of x. That irreducible polynomial takes zeta n as its root, and it has the degree of that extension would be Euler's phi function of n. But there's something else interesting here. Let me just write these formulas down. There's something I haven't told you before in this section that's really interesting. So we take the product of zeta primitive in mu n of x minus zeta. My zetas are slowly but surely becoming z's. Sorry. You're like, your zetas have been z's in my notes from the start, so I was way ahead of you. Very good. Less than or equal to a, less than n. So you could also group that as, so here's a different way of writing. This is a product notation, guys. It's a product of x minus zeta n to the a. Oh, look, so let me change the a to a j. So that you can see the explicit connection with what I wrote over here. So you take, like, the primitive nth root of unity would be e to the 2 pi I over n raised to the j power. That's like a typical nth root of unity, where j is something in the group of units. All right. So then he points out that x to the n minus 1 can just be written as the product of, good grief, can't write anything today, zeta to the n equal to 1, such that zeta is in the nth roots of unity of x minus zeta. All right? So this is not the cyclotomic polynomial anymore, right? Now I'm looking at x to the n minus 1. Yeah. Yeah, that's notation, right? So this is a popular notation for GCD, which I tend to not use in abstract 1 because I just think GCD stands out better. Yeah, but this is, Smith will use this, right? Soprano? I keep feeling it. It's history, huh? I see. Okay, so does this make sense? So if to factor, what are the zeros of x to the n minus 1? If we set x to the n minus 1 equal to 0, x is an element of the nth roots of 1. These are the nth roots of unity. So if you look at all of them, then you multiply them together, you get back. We've actually looked at this for explicit n. Like I've worked this out for n equals to 4 or something. Right? This is how we factor the nth roots of unity. Now, what he points out is something kind of exciting. He's like, what you could do is group together factors x minus zeta, where zeta is an element of order d, and like take the product and like regroup things. The product of d divides n, right? Take those ones, and then you'd have that you multiply together x minus zeta, and this inner product which was very confusing to me when I read it. The inner product. He said, the inner product. And I said, inner product? What inner product? What's the notion of distance here? No, he means the inner product. Literally the inside product. Product. Unfortunate conflation of terms. So zeta in mu d, all right, zeta primitive. All right. And what are we looking at here? This, by definition, is the cyclotomic polynomial of order d of x. So what you got is the product of the divisors of n of phi d of x. You might recognize the following homework problem. Take the order of the left-hand side. What is the degree of the left-hand side? Degree of the left-hand side is what? N. What's the degree over here of the right-hand side? If you've got a product of polynomials of various degrees, how do you find the degree of the net thing? You add the degrees together, right? What's the degree of each thing here? The degree of phi d of x, big phi of dx, is phi of d, right? So I take the sum over the divisors of n of phi of d. Remember? Yeah. Now, this is very cool because this means that we can use the cyclotomic polynomials of lower order to generate the cyclotomic polynomials of higher order. Let's see how this actually works out for a specific one. Okay? Oh, and since I'm over here. Oh, hey, this one's very exciting. Well, make room for more. Isn't that, I mean, look at that. 0200, I mean, that's very exciting. Okay, I'll stop. What? What, the 943? It's not?
It was up and then it went away.
Really? 2581. That's weird. There's a bug in their software. They don't allow for me taking attendance every 10 seconds. Why not? Okay, so note that phi 1 of x is equal to x minus 1, and phi 2 of x is equal to x plus 1. Why is that? What's the first root of 1? 1. X minus 1 is, oh, it's x minus 1. What is the primitive second root of unity? There's only one of them, minus 1. So x minus a minus 1 is x plus 1. That's where these come from. Okay? Just the definition. Phi 3, what is phi 3? Well, check this out. So x cubed minus 1 is supposed to be equal to what? I should be able to write it, what's the general rule? I can write it as a product of the divisors. What are the divisors of n? N equals to 3. What are the divisors of 3? Right. So this should be the product of phi 1 of x and phi 3 of x. But we already know that phi 1 of x is x minus 1. So phi 3 of x and that same thing is going to be true anytime we have a prime. Right? Anytime we have a prime, the only divisors of the prime are 1 in itself. Which is why for a prime we may define the cyclotomic polynomial as what? And I've told you this in a previous class, I think. We can define phi p of x as equal to x to the p minus 1 over x minus 1, quote unquote, where that's an invitation to do the long division and come up with whatever it comes out to, right? Okay, so great. So you do the long division here, and what does phi 3 of x tell you? X squared plus x plus 1, right? He has a proof that the cyclotomic polynomial is irreducible in this section. I'll let you read it, okay? I'm going to focus all of our efforts here on this recursion idea. It's really neat. So what if we had x to the fourth minus 1? What are the divisors of 4? Yeah, we got what? You said 4, 2, and 1? So that would mean we'd have phi 4 of x, phi 2 of x, phi 1 of x. And so phi 2 and phi 1, that multiplies to give you x squared minus 1. That tells us that phi 4 of x is, in terms of polynomial long division, x to the fourth minus 1 over x squared minus 1, also known as x squared plus 1, right? So there you go. That's phi 4 of x. That corresponds to the fact that how many fourth roots of unity are there? Like, how many primitive fourth roots of unity are there? There are 2. What if we, and by the way, this always works out like it worked. I mean, this is always what? How's it go? X to the p minus 1 plus dot 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 plus x squared plus x plus 1, right? I mean, that calculation is always that. So for a prime, the cyclotomic polynomial is easy enough to write down. The arguments he gives in this section verifying, in fact, that the polynomials are irreducible, and the other things he has to say about, these polynomials, really, really beautiful arguments. Sorry, we have to start our break. How about 6? What are divisors of 6? 6, 3, 2, 1, yeah? So you got what? You got phi 6 of x and phi 3 of x, phi 2 of x, phi 1 of x, all of them. Of course, we know that 1 and 2 gives us the x squared minus 1 term, and we know that phi 3 is what? X squared plus x plus 1. So we just got to multiply these two guys out. What's that give us? X to the fourth.
Oh, you know that x cubed minus 1 is x minus 1 times c squared? X cubed minus 1 times x plus 1. That's like easier.
What?
Like from the top line on the left,
Mm-hmm.
of like the word to the left, you know that x minus 1 times phi 3
Uh-huh.
x cubed minus 1. So if you pull
Oh.
1 from the x squared minus 1.
Thank you. Oh, that's a good idea. you're like, just take this and that and make it into a x cubed minus 1. And then I've just got, what's my phi 2? X plus 1, right? Thank you. So we're looking at what? X to the 4th plus x cubed minus x minus 1. And so we just got to do what? We got to take, I mean, there are various approaches. I think I'll use long division since I'm going to be, I don't want to think. So that gives me an x squared. What's wrong with me? X to the 6th, x to the 5th, x cubed, x squared. So what's that? That's minus x to the 5th plus x cubed plus x squared minus 1. I guess I do minus x, right? What did I do wrong? I mean, it's possible. So it looks like I get an x to the 4th minus x cubed minus x squared. Excuse me, not minus x squared, plus x squared plus x cubed, right? X to the 4th plus x cubed plus x squared. Oh, the x squareds cancel, thank you. I didn't see it. Yeah, minus x plus 1, which is, that's minus 1. Oh yeah, because subtraction, I mean division, right? And that is exactly that, which is good. And so we just plus 1. So therefore, phi 6 of x is x squared minus x plus 1. And how many primitive sixth roots of unity are there? 2, right? And that's their minimal polynomial. Now he gives a list out to like phi 12, and all of his list, all of the coefficients for the polynomials are integers, like plus or minus 1 specifically. But then he makes this comment on the next page saying that there exist cyclotomic polynomials with arbitrarily high coefficients, and an example is suspiciously missing. It's very uncharacteristic for this book not to have an example of that. It makes me wonder, how high do you have to go before that happens? I don't know. Maybe it's in the exercises, but with that, one more time, and then we'll call it a day. $37.92. All right, with that, go in peace.